It's a huge delight to be here today. I must say, we've been talking about the Research Computing Center for a long time. We've actually been doing something about it for a somewhat shorter time. Barali and his team have each put in about 5 years' work in the year and a half or so that they've been here. And finally it's happening. We're bringing this forth and we're actually going to have a Research Computing Center. It's very fitting that we're in this room. The Research Computing Center is all about partnerships. In some sense, that's all it is. And one of the most productive partnerships in the beginning has been the partnership with the library around the Kathy Czar visualization room. I'm very pleased that the library has done this, and I'm very pleased they're having us here to host this event. So thank you very much. The second partnership, which has been enormously productive, has been with IBM, and it's a great delight to welcome our visitors, John Kelly and his colleagues, Tilak Agrawala, Michael Rosenfeld, James Sexton, and Dave Turek. The partnership with IBM goes a whole lot deeper than a vendor and a customer, although that's a piece of it. We bought an IBM computer, and I hope it goes farther even into the future. There's a huge synergy between what the university does, what Argonne National Lab does, which is of course part of us, and what IBM does, which we've been developing. IBM has been extraordinarily helpful in setting this up, and the fact that the team is here today shows the interest, and I hope this develops into the future, so thanks for coming. Another partner in this project has been Information Technology Services, Clara Yelenkova. Clara, who is the director of that, Clara was a part of the RCC before we even knew about Barali and before she was part of the University of Chicago. And much of the work that preceded the founding of the RCC, we had advice from lots of people, including an external advisory team, which she chaired back when she was at Duke. Gave us very good advice, and I think we've used that advice to good advantage. And I'd like to think, at least a little bit, that Clara got introduced to the University of Chicago during that exercise, and the University of Chicago got introduced to her, so there was extra beneficial fallout to all parties. And of course, our principal partners in all of this, the faculty at the university and the scientific staff at Argonne National Lab, where without that, I mean, that's what the RCC is here for, is to promote their endeavors. And I'm pleased to say that already, even before the birth of the RCC, they are partners in this. There are faculty who have, during the recruitment process last year, have talked to Barali and his team about what would happen to their computers when they came here, and apparently got satisfactory answers because they showed up. And there are partners on the faculty who actually, what we're celebrating in some sense is the opening of Midway, the first cluster that RCC has, and around Midway, which the center paid for, are cores which faculty have paid for because they think that's the best way to do their computing. So I think already we're providing a service to this. I should mention a little bit about particularly the partnership with IBM. As I say, among other things, we happen to have an IBM computer. But beyond that, we have a research ambassador here who is helping us to look for synergies between IBM and the university, which I think is very important. I think we will find these synergies. I think doing this through the RCC is the way to do it. Again, all of the work at the university gets done by faculty, students, postdocs, but the RCC facilitates a good piece of that work, and they know everything that goes on. Barali, in the year he's been here, knows more people than I do, and I've been here 45 years. So the RCC is just all over the place. They know what goes on here, and this is a good point of contact. The concept is one-stop shopping, not that the RCC can do everything for you, but they know everybody who can do something for you. And I should also mention the relationship with Argonne. As I was talking to John about earlier on, the entry point there is the Computation Institute, which is a joint institute between Argonne and the university, which has worked very well. One of the things I think this is going to do, and of course IBM has a very close and intimate relationship with Argonne, certainly through the Blue Gene series and the new Blue Gene Q, but up through exascale. I mean, I think Rick Stevens eats, sleeps, and dreams exascale and maybe nothing else. And Argonne would certainly like to see this happen, and for the benefit of the nation, and certainly like to see it happen out at Argonne. And IBM are our partners in that endeavor. I have a bit of a vision about exascale and the university and the RCC. I do not believe, even in my wildest dreams, that we're going to have the exascale computer sitting on campus run by the RCC. That's not what it's about. But what I think can happen is somewhere on campus there is right now, people, faculty members who have never used a computer for anything other than to read email. But as they go about their own work and develop their own ideas, they will realize that high-performance computing can play a role in solving the major problems they want to solve. Dealing with data sets that they don't know how to deal with, simulating large and complex systems that they have no other way of gaining knowledge about, and it will become natural. This is the sort of thing they want to do. If that's to happen, it'll start at the RCC. It'll start with the machine, with Midway, and it'll start with the hand-holding that Barali and his team brings to that. It might progress to Mira, and ultimately to the exascale machine when that comes. And I hope at the end of this whole process, people who didn't know what computing was will use these new tools which are coming along to create and execute the ideas that change the way people think about their field. That's what the university does, that's what Argonne does, and I think this is where the RCC plays into all of this. So it's my great pleasure now to turn this over to the father of the RCC, Barali Ranesha.
Good afternoon. Thank you, Dan. Thank you all for coming. Before we go to the main program, I would like to take a moment and explain what events led to the opening of the Research Computing Center. Last summer, I joined the university in the newly created role of Director of Research Computing in the Office of Vice President for Research. One of the questions, first of all, we ask ourselves, then, why have a Research Computing Center? Shortly after I joined the University of Chicago, I began meeting with faculty members and asking the question, what is the best way to support the computational needs research here? And two major themes really did emerge at that time. One first is the numerical simulation and data analysis become fundamental to research progress in many areas of science here and the humanities. Research is becoming increasingly interdisciplinary and collaborative in nature, and integration of high-end computing is now a necessity for many researchers at the University of Chicago in order to stay at the forefront of their disciplines. Second, it was clear that faculty, staff, and students lacked access to the infrastructure and training that they need. And graduate students, for example, could install machines and Linux in their labs, but the expertise, the time and effort they were really putting into, and that is required to master modern HPC architecture, was really completely prohibitive at their level. With the issues defined and the guidance of faculty members, I decided to formally organize support for computation under the Research Computing Center. In December of last year, we launched the first version of our website as a beginning, and initiated the procurement of the advanced computing infrastructure which eventually became what we call Midway. And a year later, our team has grown. The procurement and deployment of Midway is complete, and I'm pleased today to say we are really ready to provide services. The mission of the Research Computing Center is to advance research and scholarship at the university by providing access to centrally managed research computing resources, consultants, education, training, and deployment of advanced technologies. What I really want to really emphasize, and what we are trying to do here, is not just to provide access to hardware. It's really to work with you to understand your research and integrate high-performance computing into it to achieve our major goal, which is to help you literally transform your research by performing computational analysis that would otherwise not be possible. The steps we've taken to do this include implementing cluster and consultant partnership programs, building a data visualization lab, a recurring hands-on workshop series, and to the extent possible, assisting porting, developing, and optimizing code to run on high-performance computers. In summary, we have created a research computing center to give faculty members here a destination, a one-stop, a go-to place for your questions related to research computing. There are three things that I see really looming on the horizon that we think RCC will be tackling. Like was mentioned earlier, the growing complexity of computer architectures, how to use them, how to program them, the deluge of data that is coming from experiments, observation, and simulation that is really creating a computational complexity that we faculty are facing in a daily, every day. And third is really the need for what I refer to as domain experts. These are staff that are experienced in both primary research as well as computing and visualization techniques relevant to their field of expertise. As computing continues to play a critical role in research, it will have a profound and transformative effect on literally all disciplines and divisions on campus. And as we roll more services and we continue to improve and refine our current ones, partner with all units on campus, we count on your feedback and are looking forward to working with you to advance the research development at the University of Chicago and beyond. On the program today, we have a panel discussion on research computing and transforming research and scholarship. But I would also like to take this opportunity to introduce Dr. John Kelly, Senior Vice President for Research. We are really pleased that he could be here today with other senior executives from IBM. Dr. Kelly received a Bachelor of Science degree in physics from Union College in 1976. He received a Master of Science degree in physics from Rensselaer Polytechnic Institute in 1978 and his doctorate in material engineering from RPI in 1980. Dr. Kelly is Senior Vice President and Director of IBM Research. In this position, he directs the worldwide operation of IBM Research with approximately 3,000 scientists and technical employees at 12 laboratories in 10 countries around the world, and helps guide IBM overall technical strategy. Dr. Kelly has received numerous technical and business leadership awards, including some of the industry highest honor. Dr. Kelly, we are really delighted and honored for you to be here today and look forward for your comment. Thank you.
Well, thank you, Barali, and thank you, Don. It is wonderful to be here with my colleagues from IBM. I was saying to Don, though, this is like preaching to the choir when I look and I see guys like Rick here. Look, congratulations on achieving this center. We think it is absolutely the right vision to have such central capabilities that are shared, sharing state-of-the-art capability for faculty. We're delighted, of course, that it's a blue IBM computer. But beyond the hardware, I agree, it's not about the hardware. It's about bringing together all the capability of the stack, including the intellectual capability around such a center. And hopefully what we'll achieve with centers like this around the country are breakthroughs from an interdisciplinary approach. And I'm delighted that we're starting to see that occur here around this center already in its early days. But I think the other thing that this center brings is it allows the opportunity for us to deepen our collaboration between the university, between IBM, and between the National Lab. This is something where we've had fantastic relationships before, but we fundamentally believe in IBM and IBM Research that our future lies in such collaboration. The difficulty and the challenges of the problems that the world faces, much less we in the information technology industry, are just too large for any of us to solve individually. And we need these kinds of collaboration. I was thinking on the way out, we often brag in IBM Research that we have 5 Nobel Prizes. I think you have 6 times that in just the physics department, Don. So we are delighted and humbled to be working with the University of Chicago. And then our relationship with Argonne National Labs has been, I think, a model for industry-government collaboration. Again, we were talking on the plane on the way out. It's one where we both respect each other, we test each other, we push each other, we pull each other through the best of times and worst of times. But in every case, what we end up with is much, much greater than the sum of the parts of our individual capability. So we just love this collaboration. We think the center is another place around which we can build and enhance our collaboration in what is really, I think, a tremendous three-legged stool between the university, Argonne, and IBM. So we as a team, again, congratulate you, and we look forward to doing much, much more with you all. And with that, again, I'm very proud to have my team here to discuss where we're going. And one of the things I'm sure you'll get into is exascale. Maybe Rick doesn't sleep at night. He thinks about this all the time. That's 2 of us, Rick.
I try to sleep in the day.
Catch a nap during the day. Look, I want to reiterate IBM's commitment to taking high-performance computing to the next level, to the exascale. This is something that is core to our strategy. It's core to our business. We are seeing now not just universities and national labs demanding these advanced computer systems, but we're starting to see it in literally every industry, whether it's the financial sector, healthcare, oil and gas, natural resources, retail, you name it. Every industry now is looking for systems of these capabilities. And it's occurring for many of the reasons that Borelli and Don mentioned. It's no longer about just computer modeling of materials and other sorts of reactions. It's about massive data, massive analytics, and extracting usable information and actionable information from massive, massive amounts of data. And so we're seeing not only the technical challenges, but the business opportunity growing in front of us, literally at exponential rates as well. So we're thrilled to be part of this, and again, we would not attempt such a mission without such great partners as the university and the lab. So I wish you all the best with this lab, and I hope that we can find other areas for collaboration as we move forward on the path to exascale. Congratulations again, and thank you.
Great, thank you. Now I'd like to introduce our panel. Charlie Catlett is our moderator, and he is a senior computer scientist at Argonne National Laboratory and a senior fellow of the Computation Institute. So Charlie, I'll hand it over to you.
Okay, thank you, Jasmine. We're going to have the panelists introduce themselves as they answer questions. That way we can get right into some questions. It wasn't much more than a decade ago that the University in Argonne created the CI, and Rick was at the center of that. And the idea was to promote interdisciplinary science, having computational scientists work with domain scientists. Having a high-performance computing central resource is new to the university. So I'd like to ask any panelist whose first name is James to maybe comment on some of the new kinds of interdisciplinary science we might see, or maybe some new services that we might see grow out of the RCC.
That would be me. My name's James Evans. I'm a sociologist here at the university, and also work as a fellow at the CI. And I'm excited to be here and talk about some what I see as kind of emerging data and computation opportunities in the social sciences, and I think in the sciences more broadly. So I think for socially relevant data, and certainly for data more broadly, there are a number of emerging trends that I think bespeak the kind of the future of the increasing power of computation in research. So one is as a social scientist, I mean, just social network data, right? Structured network data about interactions at really large scales, hundreds of millions of nodes, billions of connections, different types of connections, so Facebook, LinkedIn, Tumblr, but also, all of the other natural platforms in which people are purchasing goods and interacting with one another in kind of real contexts on the web. There was a couple of years where people in my field were really excited about these massive multiplayer games. And now it's kind of, people aren't so excited about that because, the whole world is a massive multiplayer game. And so, there's really no need to think about fictitious data. I mean, this is real data. So entire kind of areas of interaction are now just accessible, visible, traceable on the web in ways that they weren't before. Certainly the same is true for content of various kinds. So digital texts, have migrated with increasing rapidity and obviously are kind of born digital now. So, millions of articles, newspapers, books, both archival as well as the production of new formal documents, and then of course the entire informal text sector, right? So everything from blogs to texting. Much of this is available in some form, although it raises new kinds of computational questions. Sensor data. Obviously, this is true in lots of the physical sciences, but certainly in the social sciences as well. People are carrying around cell phones, specialized wearable devices, in shoes to indicate balance, and lapels for audiovisual and orientation information, embedded computers in cars and laptops, and increasingly wallets and clothing, right? So there's just this data on things that are off, things that were off grid are increasingly migrating on the grid. Also, there are opportunities and changes in the scale and the direction of experimental data. So I'm a social scientist, and yet most of the questions that have received kind of experimental treatment in the past have been very, anemically social, right? So they've involved experiments with 2 or 3 or 4 people. I mean, that's kind of an impoverished social. So the emergence of ubiquitous computing platforms increasingly allow entire groups, networks, crowds to kind of be recruited at scale, where a host of other kinds of behaviors can be reported. New experimental treatments can be designed. Streaming data, so obviously real-time computation has been something that that people in military intelligence have thought about for a long time, but increasingly it becomes relevant for running cities, for organizations. Effectively, anything that really puts findings to work in this analysis framework requires some real-time computation. The fact that increasingly machine learning protocols are available that allow us to classify things, and one huge part of the data the data exercise or the data analysis exercise is kind of curating data, making sure that it lines up, cleaning the data, putting together complex, multiple data sources. And increasingly, I believe machine learning protocols will be used to to automate this, to recognize, names and dates and these kinds of things. And so really to allow researchers to ask questions rather than just, kind of muck around in the details of the schema of the database that the data's in. Also, increasingly, with huge amounts of data available for answering questions, the bottleneck actually becomes the questions. And so I think there certainly going to be, and you can already see in some cases, opportunities, increasing opportunities for computation and kind of data mining to really look for new questions. In a small data world, there was a huge concern, certainly in the social sciences and also in many other sciences, that data mining, so just kind of looking for associations, would corrupt what little experimental or well-curated data that you had, so that you couldn't ask the questions. But in a world in which data is streaming and in much more plenitude, then it's silly not to use computation, not only to kind of curate answers, but also to kind of define questions and possibilities. And then finally, just the sociology of science. I mean, there's a larger scale collaboration in every field. So even the humanities, which we think of historically as being kind of one researcher, artisanal shops, have increasingly become multi-person enterprises. And this creates more centralized resources required by and also available for these different research projects. So I think just quickly, three things that all these kind of emerging trends push, and that I think the RCC can start to explore is one, just data size. The data size is much larger, right? In the past, we'd sample these things. In the present, typically we do sample this data, but with a structure to the data, structure that's not well specified, then that sampling typically produces answers which are not close approximations of what we're interested in. Two, data sensitivity, right? So with digital archives, that are large enough that they're valuable, there's intellectual property and copyright associated with these things, requires new models of kind of non-consumptive use where computation's going in and working with data that doesn't come out in its raw form, but is available, answers from that data is available. But this requires, really, staff and networking and computing resources that kind of, build new protocols and enclaves that are available for that. Also, more intrusive data requires more sensitive kind of layers of privacy in these kinds of archives. Sometimes there's no commingling of data, which are kind of required. Finally, if we're modeling not only the answers but also the questions, if we're modeling to mix and put together the data as well as to analyze those hypotheses that we kind of come to the data with, this is going to require much, much, much more computation. So I think for all these reasons, I'm very excited the university's investing in. I think that computation is not only going to be central to research, but that it really has the potential to transform the place of research and certainly transform the contributions to society from the social sciences. So with that, I'll...
From our interactions, James, one thing that has struck me is from the physical sciences, when we say big data, it's typically a volume I/O rate sort of problem. The problems that you're dealing with in social sciences and economics are not so much big volume, but big variety of data and from many different sources. So before you can start to ask your computational questions, you need a lot of assistance in technology to get the data to the point where it's askable. I'm wondering if James Sexton, if you can think of, from your interaction with other centers like RCC around the country, around the world, a few examples of successful new kinds of interactions, new kinds of services that we might expect and maybe demand from Birali here at the RCC.
So thank you. My name is Jim Sexton. So I'm from IBM. I lead the computational sciences team in IBM. So we spend a lot of time actually thinking through the value of the systems that we deploy and the solutions that we deploy. And James talked very nicely about the value that's coming. One of the things we see is that the center, these kinds of centers, the RCC, is really a way that you can actually consolidate a breadth of experience and skills around about a resource. The computer and the data that James talked about, that's a resource, but the way you actually extract useful information from that resource is really the expertise that you put around it. And the expertise is not just one or two people. It's a range of people who know mathematical algorithms for analysis, for optimization, for sensitivity analysis, people who know how do I structure data, how do I do graph analytics on top of data. We need people who can manage the security and the sensitivity of the data. And you need people who can visualize the data, and it's great that this center has actually tied in visualization very, very tightly into its engagements. And what happens when you think about those kinds of sets of skills in individual academic groups, it's very, very hard to build a complete stack of expertise around a single domain of application, because you may need the graph analytics once every year. You may need the mathematical analysis once every year. And it's hard to justify an investment in an individual domain research group to do that sort of thing. That's why the center that's proposed here and coming into play really has a huge advantage, because it's a place where you can consolidate expertise. The expertise doesn't all have to be in the center, but it's a place where people come together. And we see that critically. You asked the question, Charlie, where do we see that? Well, obviously the national labs are past masters at doing this kind of thing. And if you think about the large breakthrough activities that are coming out from analytics, from modeling and simulation, which really means understanding the complex systems that we have in the world today. If you think about the teams that go together and actually demonstrate and deliver value, you find that they're clustered. They're clustered around significant centers with breadths of skills. So climate modeling is a perfect example where you have a breadth of skills, a breadth of different expertise coming together, working together. We work very closely with Lawrence Livermore National Labs, and we're actually working with them together to assemble a core team working, providing sort of HPC skills out. And very quickly we found that the opportunities span from the physical sciences to the life sciences to even into data and just analyzing large data. And so what we find as we look at these activities is a constant repetition in terms of the classes of expertise and the classes of capability you need to have. And the only way we found that has successfully delivered on the opportunities is in a central activity that brings people together and allows sharing of that expertise. It's not possible for individual groups to actually assemble everything they need themselves. Okay.
Thank you. So it's kind of the same question, but I want to turn to Tilak and Rick and get some comments from you. I'd summarize the question as life beyond the top 500 list. It was 10 years ago, the top 500 list, the top of the list was the Japanese $400 million machine, and it was like smaller than Midway, or roughly the same size. I remember in 1985 we started NCSA. This Cray XMP came in, and the big story was, at least the one I remember, guys that would move code from a VAX computer to the Cray and go from 200 hours to like 1 hour. And those were not uncommon, but they're less common today. So I'm wondering, if you think about the RCC, how can the value be orthogonal to the particular hardware that happens to be on the floor? And I think I would say Burali, in capturing the goals of dealing with complexity, the data deluge, and domain experts, already recognizes the value of not tying RCC to a particular machine. Maybe one of you, or go in the order, comment on that. We go right to left audience, so Tilak.
Okay. All right, I'm Tilak Agarwal, and I'm responsible at IBM Research for all of our advanced systems work, including high-performance systems. And in that sense, I'm the odd person out on this panel, because all of the colleagues on the panel are really computational scientists or applications people, and their view is very, very important, obviously. I do not think that one needs to be successful. One can only be successful just by having the biggest, meanest hardware. I don't think that's what it's about. I do think it's about utilizing the resource, as some of my colleagues have already said, to really attempt to bring, of course, as an enabler, to the research that's being done in specific areas. James talked very eloquently about what's going on in the social sciences. But in particular, I would say trying to look at the intersection of various disciplines is going to be extremely important going forward. So just to cite an example, we can do a lot of work in the social sciences and on social networks and the like, but really big things can happen if you combine that social information, that social network information with, let's say, other information about how do you manage the electric grid. I'm just making up this example. And do a better job of optimizing based on understanding the patterns of usage through social network analysis, and using that actually to deliver the right kind of energy to the right place. I can also think of numerous examples that bring this social information together with let's say, medical information, right? There's all kinds of work going on at the intersection of these disciplines as well. So what's my point? My point really is that, yes, you do need to have all of the capabilities that we've talked about. You need to have the right kinds of codes. You need to have the right kinds of hardware. You need to have the right kind of support. But ultimately, I think if you can come together at the intersection of different disciplines, right, which will force you to look at the world in different ways, I think you will find that though hardware might be a linear improvement, that this in this other world of the intersection, 2 + 2 can become much, much bigger than 5. So I think applying sort of your collective expertise, and we talked about 16 Nobel Prizes or whatever, but combining that expertise, focusing on the big data aspects, trying to see how you can leverage big data in different areas. Each one of you in a particular discipline is looking at certain silos of data, right? My advice would be that one way to really move forward is to see how you can actually leverage this data that exists in different silos. How can you bring it together, and how can you apply techniques that you're familiar with in one discipline to help in this multidisciplinary approach. I'll end with just one simple example where obviously I'm from IBM, I'm responsible for systems. We know chapter and verse on how to analyze circuits and how to build circuits that work. Well, not very surprisingly, and we've done some outstanding theoretical and practical work in that area. Then one day we decide we want to go into grid computing. And I look around and I try to see, well, who are the people who have this kind of skill? And lo and behold, it's my circuits people, right? It's just bigger kinds of circuits or different kinds of circuits. And a lot of the work that we're doing on the electric grid right now in IBM is actually leveraging the expertise of people who are circuit designers who never thought about electric grids in their whole life, but they're doing an outstanding job. So
Thank you.
there are many different aspects. This is one aspect of how you go beyond the hardware resources that you have. Rick?
Hi, so I'm Rick Stevens. I'm a professor here in computer science and helped start the CI and Institute for Genomics, and I'm associate lab director at Argonne for computing, environment, and life sciences. So I'm trying to remember Charlie's question, but I think it was sort of how to go past, you know, the, I don't know, corporal limitations of the machine that you have. And I'm listening to everybody talk here, and I think there's a couple of ideas that are sort of at the heart of this. So, of course, Midway is a somewhat significant machine in itself. It's, you know, several hundred times larger than the typical resource somebody has in their office, right? And if you think in terms of the national or global landscape of computing capabilities. I mean, everybody has, things like this and cell phones and laptops and so on. Midway is a machine that's, hundreds of these, right? And the machine we have out at Argonne is millions of these. Okay, so you've got sort of this, a couple of hops until you're on the biggest kind of machine. And so one possible way in which RCC can help researchers, in addition to the ways that were talked about here, is by giving them a place to expand for that first, inflationary period of your ideas off of your laptop onto this next generation in an environment that has some traction with the bigger machines. So if you can get your analysis to run midway, you're pretty far along getting it running on the biggest machines on the planet. And to the degree that IBM's environment is compatible up that food chain, then that's a really good sort of technical kind of ladder you can climb. But maybe more interestingly is computation itself is a way of understanding things. And people talked about interdisciplinary this, interdisciplinary that, and what it really boils down to is you've got two people from different domains. One way to really make headway on a interdisciplinary problem is to try to write code together, right? You never really fully understand what you don't understand until you actually try to write the simulation or the analysis routine to take all the words, and we're at a university, so words are cheap, right? We can all sit here and talk for hours. But sitting down and actually writing code and trying to get something to work is where the rubber hits the road. And so wrapping around the RCC a kind of collaborative environment for groups to get together, accelerated by things like the CI and by other activities around the university, creating that environment where people can sit down and discover new things by writing code together is one really interesting way this can happen. I know that if you take the very, very broad view of applications, one end of the machine is going to be running codes that simulate partial differential equations in neutron stars or whatever, and on the other side of the machine are going to be people doing natural language translation or doing computational photography over here and doing symbolic algebra over on the other side, right? So the range of possible things that a resource like this can accelerate is enormous. And I think, it can't do everything, but it can provide this environment where the people who know how to access the global databases can import data, bring tools. I think that's really going to be the main advantage. I think I'll turn it back to Charlie and let him ask us some harder questions, Charlie.
Okay. So let me turn to the James gang in the middle here. So I've watched Rick's office library evolve over 20 years, and it started out with computer architecture and networking and grids and stuff, and now that those have not gotten dusty, but it's probably more heavily biology. So Rick's talking about writing code together. It's really an example of a computer scientist learning how to be a biologist in order to help the biology community exploit computing. And in the process, the biologist learned something about computer science as well. If you think about what you need to do your science in social sciences, or what sort of skills are necessary to really take advantage of not just computing, but being able to deal with these data, what should computer science undergraduates be studying as a secondary major these days? What sort of skills are you looking for that can help the discipline sciences outside of computer science exploit these resources and capabilities?
So let me take that one first, because I happen to be actually recruiting right at the moment, and so my preference always is somebody who has deep domain skills, deep fundamental skills in a domain, whether it's physical sciences, life sciences, whatever, but also has managed in the course of his or her career to develop some deep computer science skills as well. So those are people, that kind of person has the ability both to understand a domain in great detail, but also understand what it takes to implement a computational solution to actually address problems in that domain. And what I find when I go looking for those kinds of people, and it's kind of interesting, is there are not too many of them out there. And so I spend a lot of time speculating on why that might be the case. And prior to my time at IBM, I was a professor in the university and used to do training. And what you find very often is that there's a sort of a force when you're a graduate student that says you should focus very critically on your core domain activity. And that's where you should spend all your effort. That's how you're going to get your papers written. That's how you're going to get your next position, your postdoc, etc. And it's very hard to argue against that force. And yet at the same time, those few people who manage to actually step outside that envelope, keep their core domain going, but also find time to actually graft these extra skills on, become incredibly valuable. And so I think there's a challenge and an opportunity here and a challenge here with a center like the RCC is if one, and those of you who are professors in the room or research leaders, research team leads, etc., think about how you can get your core people doing core domain science to actually spend some time learning about the computers, learning about the solutions along the way, learning how to implement them. It's going to be incredibly valuable for them. It's difficult for them to do because it distracts from their core business. But in the process of being able to set that up, I think we would develop a very different cohort of researchers over the next few years to really take advantage of this technology, because it's not just the computing, as we talked about earlier. It's also how do I get the people with the right mindsets to work on it. So let me pass it on to James and see if he has a thought.
Well, I mean, I think certainly. I mean, there's different models to education, right? And so, insofar as Burali was genuine in saying, he hopes that the RCC is a go-to place for computational questions. The structuring of an educational infrastructure is going to be very difficult, right? Because at one level, one could kind of imagine, a set of computational and kind of data skills which are generic across all fields, but it's kind of hard to imagine how informative those would be. The ones which are generic across all fields, right? And so at some level what it requires is it's going to require domain experts to really invest in the computational skills which are required to port their questions onto into computation and to and to work with their kinds of data and to analyze their kinds of data in these settings. And so I think, the kinds of things that Burali's been doing, the kind of the shuttlecock diplomacy, talking to people, figuring is one step in that direction. I think another is going to require really some investments from domain scientists who are committed to this as a possible future and to irrational investments in some sense, in these kinds of things. And I think this also speaks to a broader, I'll call it a kind of, maybe it's a hiccup, maybe it's a crisis in the way in which we think about computing, kind of supercharging, enhancing research, is just that it's really hard for computational scientists to get a return on their skills in these scientific projects, right? So insofar as they're acting as infrastructure or supporting other research, then often they're not getting the kind of the citation and authorship and all the accolades, all the intangible rewards that one gets in the context of science. But they're also not making the money that they would make in industry doing analytics for other kinds of routine problems. And so I think this is actually a bigger problem than the RCC. I think this is a problem of kind of national and international science policies, like trying to figure out ways to share credit to enable computational scientists for the investments in mixing domain and computation. To provide returns to them, which are not irrationally low. So,
could I make a comment on that?
Yeah.
So I think there is an opportunity, at least in terms of the kinds of people that we would be looking for in the future. For example, if RCC, so this is not a systematic approach, but if RCC, around RCC, one had some projects, what we call smarter planet projects or smarter city projects or smarter XYZ projects, where RCC is kind of the centerpiece of the computational side, but you've actually got faculty and students engaging with the ecosystem, right? Whether it's a city or whether it's the university, to solve some problem. Do you all understand what I mean by smarter? It really means sort of having transparency to events that are going on, doing analytics on those, creating a model of the world, and closing that whole loop, right? And we can follow up on that later on. But my point is that if you actually can engage in interdisciplinary projects which bring in part of the ecosystem for a particular problem, let's say you want to make a particular building here more energy efficient. I'm just making this up, right? Think of that as just an example where students, faculty would get engaged in analytics and modeling and simulation, but as part of a problem that includes a broader ecosystem. I think that can be a tremendous learning experience for all parties involved.
Yeah, maybe not a building, maybe try to make the legal system more fair, for example. That's a good problem to simulate. How many people here have have consciously made a decision to not work on a problem because they didn't think they could solve it with the compute resources they had available to them? Well, Ben, okay, all right, expect. So that's interesting. So that means, so how many people in this, I'm trying to figure out, so I would expect a bunch of people to raise their hand because in some sense having something like the RCC is aimed in part at trying to address that issue, right? So if you haven't not solved a problem because of the compute races, how many people didn't solve a problem because they didn't know how to solve the problem? Okay. So in that sense, the computer may help you or may not help you. I mean, Charlie and I were talking before the meeting about, could we imagine the future? How could these machines be so easy to use that you wouldn't need to have programmers, for example? And I said, well, we already sort of have that. They're called grad students, but you have, they sign up to get something in return. But if you had a machine that was really intelligent, you'd probably have to bribe it in some way, right? You'd sit down and offer to buy a latte if it would solve your problem, or maybe you'd have to convince it that your problem was really worth solving in some way, in some discourse. And I think, of course, the RCC wouldn't be that helpful if before you could use it, you had to convince the staff that your problem was worth solving. But in fact, that's probably the best strategy to get more than your fair share of staff to work on your problem. Just have a problem so compelling, or at least your story of the problem to be so compelling that all of Borelli's staff and some of people that aren't Borelli staff would be joining with you to work on that problem. I mean, my experience when we get faced with new machines, and this happens over and over again over the last 20, 30 years, what happens is that you have a problem maybe in the back of your mind that you didn't even know you wanted to solve because you didn't really think it was possible, or you didn't think that it was important. And suddenly you have a resource now that in some sense is like a much bigger blank piece of paper. What can I do with this, right? And I think the challenge to everyone at the university, now that we have this center, is to think a little bit more expansively about what they can do, and let the Borelli staff or people they can drag in tell them when enough is enough, but to be very aggressive in asking for capability. And I'm sure that if we oversubscribe the machine by a factor of something, we can get a bigger machine, right? So
Yeah, I was gonna, I noted that, Tilak, when you were describing the machine, you said biggest, meanest hardware. Maybe a Freudian slip that these things are not the most friendly things to use. And so, I may for all the panelists, just following on Rick's comments, when can we expect Watson for science? I mean, when can we expect to be able to interact with a machine in a much more natural way? Maybe we don't have to bribe it with a latte. Actually, I was told by Apple yesterday, I sent a machine in for repair, and they said if we have evidence of liquid being spilled, the price goes up, by factor. So maybe you don't want to put latte
And
in your machine.
they have sensors in these now that you detect when you've poured latte on them. Yeah.
So
Only latte.
So, I mean, this is actually an opportunity, I'd say, there are other folks from IBM in the room as well, to ask, what is it going to take to get the kind of natural interaction with a machine that we see, at least in demonstrations, so that the machine can actually guide the scientist in how to think about their problem and how to think about questions that maybe didn't come to mind.
You said by when, right? I don't know exactly by when, but how many of you have heard of Watson? All right, good. So Watson is actually a Q&A system that you query it. You ask it a question and it gives you an answer. Most of you must have watched the Jeopardy match. Seems like yesterday, but it was a while ago. Now, it's not that inconceivable that very soon we will be able to handle both different kinds of data, not just natural language data, but streaming data of a variety of different types that James was talking about, unstructured data of multimedia data. And it's not inconceivable either to add the kind of modeling and simulation capability that we already have, that we're very familiar with in the high-performance computing world. So it is possible that these things will start coming together. But in my opinion, that's still a ways away. And in between, I think the big challenge is really how do you make these systems more programmable, right? Easier to program. And especially with people like Rick Stevens around, I hope that a big piece of this effort would, or at least a part of this effort, also brings in computer science folks. Borelli, I hope they're involved with this as well, so that getting the right kinds of tools, creating the right kinds of tools that help with programmability is something that's going to help you and other people. And the other piece that Jim Sexton referred to just a little bit was I'm very, very fundamentally convinced that even before we get to a sort of Watson-like Q&A system, visualization and what we are now calling visual analytics is going to become extremely important. And I'm very happy to see that there's a strong visualization component to this whole exercise. So there are marvelous things that you can do if you have the capability to actually bring multiple different data sets together like we've been talking about, to really be able to visualize them in different ways, to be able to steer the computation or the analytics that you want to do on the data based on the data that you're looking at. I think tools in general, and in particular visualization, is going to have a big, big impact on the usability of these machines, because like we've been saying, it's going to be a lot about data. And I would also say that yes, it's not too far away that you might actually have a Watson-like Q&A capability. And in fact, in the medical profession, we're already starting to use Watson to answer certain questions and help physicians and help nurses in unimaginable ways. We do not have enough time to go through all of the learning that we've had in the last year or so, but the sky's the limit, really. So there's reason to be hopeful.
I was just thinking that wouldn't it have been great if the original Jeopardy was like Jeopardy for physics or Jeopardy for doctors or something? Then we'd already be there.
Well, we wanted to reserve a little bit of time for those of you who came over to interact with the panel, ask a question, or maybe answer a question like, gee, that's a really neat thing that we have this big machine, but what would really help me is if Barali would fill in the blank. Do you have a question, anyone, that you'd like to ask of any of the panelists or of the panelists as a group? Benoit?
There's often a kind of a tension between calculation that harness parallel computing in a highly coupled fashion versus loosely coupled. And highly coupled is, of course, I believe, technically much more challenging in many ways. What's your view on that in terms of long range? And, you know, if things have to become much more accessible to a wider public, my impression is that seeking solutions that will be loosely coupled perhaps are easier to implement in general, but perhaps not every problem can be solved by that. I don't know what you think about that.
I would agree with that. No, I mean, I think that as we go forward, we're going to have an explosion of underlying silicon capability. So we will have cheaper, low-power devices, billions and billions, trillions of them, right? And the vast majority of them will be connected in some way, but a very small fraction will be coupled and engineered to act as a tightly coupled supercomputer, right? So to the degree that a problem can be mapped against the broader infrastructure, whether you call it a cloud, whether you call it streaming, you know, whatever, I think we will see that because that will be the cheaper, more ubiquitous design point. I think the fundamental challenge for computational scientists or algorithm developers is how to broaden the class of problems that can actually be solved in that framework, right? We're making very slow progress in that. Maybe we'll have some breakthroughs. I don't know. I mean, it's you know, where high performance computing has grown out of essentially computational physics, and there's been two branches, as you well know. I mean, there's very loosely coupled problems, Monte Carlo type problems that are easily highly parallelizable on distributed hardware, and very tightly coupled problems that grew out of other kind of computational physics that are resisting that kind of thing. And I think that both will be important, but I think the loosely coupled one is really unbounded in its potential right now.
Yeah, Jim should probably really expand on this. I'll just say a few words and then maybe Jim will jump in. But as we get into optimization problems, right? So you're trying to optimize design as you're trying to become prescriptive in analytics. It becomes important to be able to run. It's sort of a embarrassingly parallel problem. Becomes an embarrassingly parallel problem because you're essentially running the same computation but against different initial conditions. You might think of it that way, right? So within each of those computations, it might be very tightly coupled, and I know I'm not doing justice to this, Jim, but it turns out that as you move to this higher level of predictive capability and optimization capability, that it becomes easier for people like me, because now the solution is inherently parallel, because you're running you're running basically the same computation against a whole bunch of different initial conditions doing sensitivity analysis. Jim?
So I agree. I mean, what we're seeing really is what's emerging now and dominating all of our thinking is the scales of data you have to manage. And the questions you're asking, because of this explosion of silicon that Rick mentioned, you're asking much more sophisticated questions. Those questions require much more. I mean, they depend on having that silicon there, lots and lots of silicon. They generate and both use and generate huge amounts of data, and now you have to have systems that can work on that data and do all the different kinds of things that you want to do to address the questions you're asking. And what we're seeing is that that's a broader and broader set of things. So the explosion of silicon, the availability of sensor data, the kinds of data that's coming off, we talked about earlier about social, is just growing the scale, but also growing what you want out of it. 10 years ago, it might be nice to do a paper that had 1 point calculation. Today, that's just not acceptable. And so that's putting a huge demand on the types of system, the integrations between the system, how things talk. And then the very fact that it's really hard to move data. If you've had to try and move a terabyte of data from one computer to another, you know how hard that is. We're talking about 1 million times that, 1 billion times that in data. And so I think we're in a very disruptive phase right at the moment in terms of systems architectures. We're really thinking through new ideas because the silicon is giving us so much more capability. And so tightly coupled, loosely coupled, they all have to go together and they all have to address and manage the data that's coming out. So.
Can I just mention one thing? I think this speaks to the education, kind of the data computational education component. I mean, for researchers to understand fundamentally which are trivially parallelizable problems and which ones aren't, which ones actually have, extremely high ceiling in terms of their ability to kind of immediately use compute, and for the compute to kind of recognize and scale up from a small box to, something, to the largest supercomputers. Just that simple education, I think, would go an extremely long way in terms of allowing people to kind of really push their disciplines.
That is the goal.
Sure.
Absolutely the answer, yes. Now, is it going to be instantaneously, immediately easy? No, it takes work, but it's actually the next step. That's the point we're making, is that you need to do that on your laptop. That's a requirement. That's how you work. And yet the data can be too large now to fit on your laptop or fit on your workstation. It has to be somewhere. That's where Briali Center comes into play. And Briali has to deliver all the infrastructure and all the software and all the interfacing and all the privacy and all the security to allow you to work on your computer, on your laptop, and actually, so Briali has to solve all of the problems.
I mean,
so good luck with that.
But there. I mean, he does have access to help, though. I mean, one of the ideas is this concept of software as a service or data as a service, this whole notion of packaging things up, packaging databases up and computational analysis pipelines as services. And then the question becomes, how do those services get integrated with a compute cluster like Midway and then delivered to the end user? And there's many projects now that are working on tools. I mean, I'm working on several of those in computational genomics or in metagenomics and in infectious disease, where we have nearly a petabyte of data, and yet we want to have thousands of users able to do complex analysis on that data in their own trajectories. And so it requires not just large-scale compute servers and databases and cloud kind of backends, but high-performance clusters that can run well-defined workflows, well-defined analysis packages, but then wrapping all of that in a way that an end user is sort of not really aware of the fact that what it takes to make that query happen, right, is a lot of magic behind the scenes. And I think the challenge that Burali will have is how to position RCC in that ecosystem. What are the class of problems, class of capabilities that he can offer as a service, and how can he interface to these public databases and the private databases and the clinical databases and so on to do that?
If I might just comment on that, I think Rick is correct. RCC is to try to integrate, and actually a good example is a tool that has been developed at the Computation Institute, Globus Online. For us is, can you make it as a service? In other words, today you get an account, you use Chicago account, but when you get an account at RCC, what you don't know, you already have automatically Globus Online credential, which means you can bring that automatically on your laptop at the click of a button. So the key is to take the tools that are being developed, how do you then integrate with this ecosystem and then to make it transparent? I think that's the vision and challenge.
Yeah, it's not your father's supercomputer.
Ken in the back of the room.
Yes. First I want to say I'm not at all surprised at the answer to Rick's question. I'm an economist, and the economists are so brainwashed to internalize hostility against computation that they actually believe that their laptop is adequate to solve any economics question they have. And Jim Sexton's comments about the academic world not producing the kinds of field experts. They certainly aren't producing any field experts in economics. That would be of use at IBM. Now, the University of Chicago is almost unique in that it actually teaches numerical analysis methods to their economic students. I teach it, of course. This is that's done almost no other place in the United States. And so with the RCC in place, that's a great benefit to that effort. But there's another problem here for social scientists in general. Vice President Levy referred to using Midway as a stepping stone to Mira. And yes, that's a nice option for physical scientists. It's not there for social scientists.
Actually,
let me finish, Rick. I had a conversation with Dan Hitchcock, who's the boss.
He retired.
He retired,
Ken.
Last March, new information has happened. Last March, Dan Hitchcock, the head of the DOE supercomputer program, said, yes, that's right, Ken. I've been hearing this for many years, and that last March, that yes, anything having to do with social policy, such as optimal tax reform or health care reform, that's policy, and that's verboten on the DOE machines. Now, hopefully that could change. Maybe Rick has some news for me, but that is a problem for social scientists. Now, in terms of like, so for right now, for social scientists, Vice President's comment about our Midway being a stepping stone of Mira just doesn't apply to us.
So I would temper that a bit. So the program that accesses or that allocates time on the DOE, the two DOE leadership machines, is actually domain agnostic. As long as the research is going to be published in the open literature, it doesn't matter where it's coming from. It could be social scientists, it could be biomedical, it could be computational poetry, doesn't matter. In fact, one of the early applications at the Oak Ridge machine was Industrial Light and Magic, optimizing computer graphics algorithms for movie production on that machine. So I think Dan may have misinterpreted. If you're trying to ask Oscar for funding for your work, policy work they will not do, because DOE, Office of Science, doesn't fund policy work. But access to computers under the Insight program, by the way it's administered, is completely agnostic. They may have a hard... Yeah, I understand, but Dan didn't put that program in place, and he's not there anymore, so we shouldn't overly emphasize Dan's comment. That program is open to anybody in the U.S., even international collaborators have access to it. So let's give it a shot. If you want a large-scale problem in optimal tax policy, let's try to get it through the system. Yes. I think the real challenge in these really large computational projects like on Mira is Insight expects the Insight program expects the application to be able to use a very significant fraction of the machine. And on machines that have order of 1,000,000 cores, that may limit the class of applications that people can demonstrate performance on, because there's a component of the review that's scientific merit and so forth, and maybe not artistic merit, and then an aspect of the review that's technical feasibility. But Barb Helland is the acting director, and maybe you want to come to Washington and serve the DOE in some capacity. Good.
I think I saw another question over here. Go ahead.
So in the university, you have these sort of cycles of centralization and decentralization going all the way back to the centralized mainframe, moving to the workstation, the laboratory. That's for hardware reasons, but also for reasons of expertise. It sounds like with some of the challenges of high-performance computing, as well as some of the hardware challenges, is this the last sort of centralization, and there won't be a decentralization back into HPC resources and skill sets into the lab?
So these things go in cycles based on technology, right? If you remember when these guys started at IBM, big IBM mainframes were centralized by definition. And then you had microprocessors, which threatened that in some way initially. And then people realized that, well, we need to have both. I mean, this is a totally decentralized infrastructure. I mean, from the end user standpoint, there's, of course, big servers out there in the cloud that are centralized. But the idea that every person's lab will have a small cluster in every lab at the campus, where you'd have hundreds of these small clusters, that's a nightmare in various ways, right? You can't plan for it. You can't support it. I mean, if you've got, 70 groups at the university, each of which are paying grad students to administer machines instead of work on their dissertations, that's not a good use of support. And, it's a cybersecurity mess. It's a data infrastructure mess. I mean, so I think the consolidation phase that we're in right now, and I'm not speaking for Borelli, it's his strategy, but I think that makes a lot of sense because it makes economic and sort of support and security sense. But it's possible to imagine a new class of devices, right, that could emerge where the community will move much faster on it than the centralized organizations. And then we'd end up in another cycle where those things will proliferate, maybe like, genome sequencers or something, or whatever, but they'll proliferate before the bureaucratic system realizes a more optimal way of actually supporting the community. And I sort of look forward to it. I think it's going to be interesting to see what that new thing is.
So I agree with Rick. I mean, right at the moment, the pressure is to centralize because the systems are incredibly complex. The value is very strong, but to deliver that value for technology reasons, you have to use lots and lots of individual processors, and you have to find a way to hook them together. You have to write really complex codes. In a few years, if Tilak is right, we can move to a different model where it's all done, there's automated tools already in place, and then maybe there's an opportunity then to decentralize again. Right at the moment, the value and the technology says it's hard, but huge opportunity, and so the value is to assemble centrally.
Yeah, I don't see the decentralization anytime soon either. So I think you should stick with the consolidation policy for now and make it work, and if things change, we'll deal with it then.
I think that's a good place to end. I'd like to thank the panel.
I'd like to thank as well the panel for this very important beginning and opening. I think it's an indication of the interest at the university. We do still have a second part of the event. There is a reception outside. I invite everybody to the reception. But we have also three things that is going to be happening in this data visualization here. We're going to also show some of the early results of some 2D and 3D data visualization. Some of these were run using Midway. Some of these are using, as I said, visualization is growing into becoming a tool for analytics. There will be two tables outside as well. that we have some stuff around that you can ask questions on how you can have access and use resources at RCC. The one thing I want to also echo, we've achieved a lot. We were not able to do it alone. This has been really a result of a collaboration, and I'm really thrilled by the partnerships we'll be able to make here, and in particular, those with the library, IT services, Computational Institute. As we say, a destination, a one-stop, think about all those institutions that are really behind it. I think we are trying to coordinate our effort to be able to address your needs. I think it's really a good example that things can work together, and we are really thrilled and looking forward to continue working together. I would like also to finish by saying none of this were able to be possible without the people who planned this event. I think I have a long list here. I don't know how much I could thank them. Liz and Jasmine, Lisa, and everyone, the list going on. I think thank you very much. And please, all of us, enjoy and welcome again. Thank you.
Thank you.